Hello again, my name is Tom Irvine, and I'm the instructor for this series of shock and vibration webinars. And I again thank Dr. Curtis Larson and the NASA Engineering and Safety Center for making this series of webinar units possible. And the title for today, the topic is Rectangular and Circular Plate Shock and Vibration. And this is for the bending mode vibration. So we're going to model the plates as continuous systems. Now another way of modeling plates and other structures, which we'll be talking about in future webinars, is the finite element method, and more about that later on. And we're first going to perform a modal analysis, or you could say a normal modes analysis, on these plates to find their natural frequencies, their mode shapes, and their participation factors. Then once we've done our modal analysis, we're going to subject these plates to base excitation, which is perhaps more formally called, more accurately called, enforced acceleration along the outer circumference or perimeter. And we're also going to take a look maybe just briefly at the stress-velocity relationship for plates. Now, if possible, we like to take our governing partial differential equation of motion and to solve that equation of motion with exact displacement mode shape functions. And we can do that for some very, very specialized, well-behaved boundary condition cases. But in other cases where our boundary conditions are a little more complex or a little less friendly, we have to use another method. And the method that we're going to use is the Rayleigh method. And the Rayleigh method will allow us to determine the natural frequency as well as the mode shape. And it's really quite simple. First of all, we're going to neglect any energy dissipation, so there's no damping. And we're going to take the maximum kinetic energy and set that equal to the maximum potential energy. And to do this, we have to assume a mode shape function. And then once we calculate the two energy maximum values and set them equal to one another, the natural frequency will fall out from that calculation. And if you'd like to know more about the Rayleigh method, I have a paper posted on my blog that you can go over to get further information. But just to give you kind of an overview here, again, the Rayleigh method requires an assumed displacement function. And we're only going to do a single degree of freedom analysis. So we're only going to assume a single displacement function. Now, if there were a need, we could do an extension to the Rayleigh method, and that's called the Rayleigh-Ritz method. And we're not actually going to cover that today. Maybe in a future webinar we will. But the finite element analysis method, which some of you are familiar with, is actually an extension of the Rayleigh-Ritz method. So I will mention that. Now, with our assumed displacement function, it's important that it satisfies the boundary conditions. Now, there's actually two different types of boundary conditions. There's the boundary conditions of displacement and slope, and those are the geometric boundary conditions. And it's essential, or it's very important that our mode shape, our assumed mode shape, satisfies those geometric boundary conditions. Now, there's also another set of boundary conditions, and these relate to the bending moment and the shear at the boundaries. And if possible, our mode shape, our assumed mode shape, should also satisfy those boundary conditions as well. But at the very least, they need to satisfy the geometric boundary conditions. Now, the assumed displacement function will introduce additional constraints, and that will actually increase the effective system, the effective stiffness of our system. So the Rayleigh method will yield an upper limit of the true fundamental frequency. So as I sort of thought about that and scratched my head a little bit, I thought, well, we can come up with a family of candidate displacement functions and that satisfy the boundary conditions as well as we can, and run them through our Rayleigh method, which I kind of briefly outlined on the previous slide, and all these things being as they are, then our most accurate mode shape from all those candidates, in other words, the winner, will be the one which yields the lowest natural frequency. And by applying some engineering judgment, we can make that work. So for some of my programs here, in fact, we actually did one last time, I should say. Let's see. So last time we took a look at a rectangular plate that was point supported at the four corners. That was in the previous webinar unit. And although I didn't really go into details at the time, I will tell you that for that particular boundary case, we were using a Rayleigh method. And we're going to use a Rayleigh method again today because we are going to have a plate that is fixed free. And more about that here shortly. So to get started with what we're going to do today, let's go to our vibration data GUI. And let's see what we're up to this week. Version 6.4. And we have this, we've actually run this before. Let's go down to the bottom corner here, right near the right corner, and let's import data to MATLAB. So we're going to have two arrays that we're going to import. The first is going to be the very familiar NavMat PSD specification. So let's read that in. It's PSD frequency in hertz and g² per hertz. So that's now read in, and it's called navmat_spec. Then we're going to select another library array, and this is a synthesized acceleration time history that we've also used before that satisfies an SRS with a 1000G plateau. So it's going to be called SRS 1000G_excel, 2 columns, time in seconds, acceleration in Gs. Okay, and we can, just to verify, we can go to our workspace, this little corner over here, and we see that those two arrays are available in our MATLAB workspace. So we're going to do some more things here. Let's go on to the next slide. So we're going to consider a rectangular plate. It's going to be 12 inches by 8 inches by 1/8 of an inch, and it'll be rectangular with fixed free boundary conditions. And we will be using the Rayleigh method for this case. So I'm going to demonstrate this in class, but I have a path on how to get to this dialog GUI in case you need to remember how to get there. But I'll just go ahead and show you how we're going to do this. So let's see, let's get back into our vibration data, the main dialog page. Let's go to structural dynamics. Let's go to plates, rectangular and circular. And we have an option here, rectangular plate, fixed free. So let's perform an analysis on that plate. So this program calculates the fundamental bending frequency of a rectangular plate with fixed free boundary conditions. The units are in English. Aluminum material, so the material properties are a preset for aluminum. And we could have the option of adding non-structural mass that would be spread uniformly across the plate, and I'm just going to skip that. We're just going to have a bare aluminum plate today, but certainly as you do these homework exercises, you're welcome to go back and try different cases with non-structural mass. You can try different materials and dimensions and so on. But for right now, let's just do a 12-inch. Now 12 inch is the fixed edge length, and 8-inch will be the free edge length, and our thickness will be 1/8 of an inch. Then we're going to calculate, and we're going to go through a series of candidate mode shape trial functions, and we're going to find out which one yields the lowest natural frequency. Then we're going to compare that with just a handbook type estimate. So calculate, it's going to take a couple of seconds, but not too long. So we'll go back to the mode shape here shortly. So here's a table, and what was going on is each time, well, here's our first candidate mode shape, had a frequency of 422 hertz and an alpha of 0 and a theta. Now, I have not yet told you what an alpha and theta are, but I will tell you later on. These just have these are just two parameters that help define our mode shape. Then each time, well, what the software was doing is it was varying these alpha and theta values to determine which pair of values would yield the least natural frequency. And I probably should show this out to two digits after the decimal point, but anyways, we come up with 420.4 hertz. That's our Rayleigh natural frequency. This is the one we're going to go with. Now, if we go to the handbook value, it's approximately about 417.8 hertz. Well, so you might say, why not just use that handbook natural frequency? And the reason we're going to stick with our Rayleigh natural frequency is because we have a corresponding mode shape to go along with that, whereas the handbook value does not. There's no explicit or given mode shape to go along with that. This will all make a little more sense as we go on, so don't try and understand this all at once. Now here is our corresponding mode shape for our Rayleigh method, and so kind of play around with this a little bit, kind of rotating around. You can just get a look at different views, different perspectives. So you can see that there are two edges that are parallel to one another that are fixed, and these edges are each 12 inches long. This is the units are inches here. And then there are two edges parallel that are 8 inches long, and they're each free. So here is the mode shape. Kind of has an interesting shape. It's got a little bit of a, I'll call this a saddle shape, kind of a saddle shape there. And it's kind of interesting with our rectangular plates, or even for circular plates, which we're going to cover in about 15 minutes or so. Our first inclination is to say, okay, the maximum acceleration, maximum relative displacement, maximum stress are all going to be at the center of the plate. Now that's usually our first suspicion, but that's not always the case, because for this particular boundary set, the peak displacement, relative displacement, the peak acceleration, and the peak stress are all going to be out at this point here, and due to symmetry, that will also be the same as this point out here. So that's just some interesting things to keep in mind with these plates. At this point, maybe just to make sure I'm being a good teacher here, I should go ahead and just give you a little more background about what we're doing. So I'm going to go to my blog for Unit 31, because we're on Webinar 31 here, Rectangular and Circular Plate Shock and Vibration. I've got a couple reference plates here that I highly encourage you to read, because these have some really good information. But let's click on this one here. This is for the fixed free rectangular plate. And I'm not going to go over this verbatim in class, but I'm just going to sort of scroll through it so you kind of get the general idea. This is the equation 1 there. That's the total strain energy, which is the potential energy for that rectangular plate. And then there's the equation 3. That's the total kinetic energy. And Z there, that's the assumed mode shape. It's a two-dimensional mode shape function. Now, if I was a college professor, I guess I'd go through all those equations one by one and would spend the whole class on those. But what I want to show you here is that this is going to be our candidate displacement function. So Z, that's the mode shape displacement, and that's equal to Vx, which is a function we'll talk about later. Then in brackets, we have 1 plus alpha cosine theta times y. Now x and y are the two dimensions in the area plane, and just through some kind of experience, through looking at finite element results of plates with these boundary conditions, and just intuition, and I came up with this function. And so you see the alpha value here and the theta value here, those values can be varied. And so the idea is to vary that alpha and vary that theta, use some random number generation to come up with these candidate displacement functions, and then run those through the previous equations for strain energy, kinetic energy, and and then see what the resulting natural frequency is. So that's what we're doing. That's our displacement function. And this is not anything carved in stone. It's not the one and only displacement function. It's just the best that I could do with the time and resources and mental energy I had available. And then there's also a function of x. It's this equation here. And this is based in part on beam theory and other plate theories, but ultimately it's just kind of something cobbled together via engineering judgment. And you can go back and read this at your leisure. I just wanted to make you aware of that. So once we have our mode shape, our natural frequency defined, we can go and do a couple of things here. Let's go to apply our base input, that's just something we love to do in this class. So you could think, for example, okay, we've got this plate, this rectangular plate with the stated boundary conditions, and it's going to be mounted on a shaker table, and we're going to apply a base excitation or seismic excitation, or if you prefer, an enforced acceleration along the perimeter. So let's enter in a Q value. We'll do Q is equal to 10. That's equivalent to 5% damping. Let's save that. And once that's saved, we have our choices here for how we can apply our base input and what type and so on. And let's go ahead and look at our transmissibilities for this plate. So this one, after some head scratching and trial and error, I decided I'm going to have a diagram here to show you where our available response location points are. So we could choose point A is right in the center, and there's point B and C there, but point D is the one where the most action is going to happen. It's kind of on this lip here. This sort of is going to curl upward as in terms of how we're representing the mode shape. So let's go from 10 to say 2,000 hertz. Will be our frequency, and let's do point D there. Let's calculate what our transmissibilities will be. So we get a couple of plots that come up. Of course, we have in our command window here, we can get the peak values here. These are the peak values at the fundamental frequency. Now, our natural frequency is 421 hertz, and that is going to have a peak transmissibility, if you allow me to round up, of 16 G out divided by G in. And you can see this if we kind of backtrack through the plots here. So that's this point here. Well, that's the power transmissibility. Okay, here we go. So this point here, and we can even put a little cursor thing, a little marker there. That's our peak transmissibility. It's happening at 421 hertz at that point D. But our Q value is 10, so we cannot pick out the Q value by simply saying, okay, let's take the peak transmissibility at resonance and go over here, and that's our Q value. Because this is a continuous system, and there's a bending gain, a modal bending gain scale factor that's coming into play as well. So if this were a simple spring mass system, then yes, we could take the peak transmissibility at resonance, and that would be equal to 10 because we have a Q is equal to 10 damping system. But since it's a continuous system, that rule no longer works. We could do, and this would be a good homework exercise, we could do a half power bandwidth method on this peak, or it's also called a minus 3 dB bandwidth method. And if we did that, we would find out that, yea verily, we have a Q is equal to 10 or 5% damping equivalent, which is equivalent to 5% damping. And by the way, if you're a motivated student, you can save the FRF and then go through the damping calculation if you like. Actually, you could just do it off this plot, but if you want to do the curve fit method that we have in another function within this signal package, then you would save your FRF. But we're going to skip over that for now, just for brevity. So that's the acceleration response function. Now, this is a typical pattern we've seen before. At lower frequencies, our plate tracks the base input with unity gain. then as we approach the natural frequency, we get this dynamic resonant amplification effect that occurs. And then beyond a certain point here, which I think is going to be, it should be about 420 hertz times the square root of 2 or thereabouts. Beyond that point, we start to filter out energy. Now some of that filtering is just an artifact because we only have one mode that we're representing. If we included higher modes like do a Rayleigh-Ritz, then we'd see that there is some amplification occurring at higher frequencies. But we're going to be content with just a single mode because, for the most part, about 90% of the stress and pseudo velocity are going to be tied up in the fundamental mode anyways. And then there's a couple other plots. This is actually the same plot that we just saw before, only now it's g squared out over g squared in, so we call that a power transmissibility. And again, this is at point D, which I'm calling x is equal to 4, y is equal to 0. We've got the two bending stress components, SXX and SYY, which get fed into the von Mises calculation. There's shear stress. Shear stress is kind of boring. Here's our von Mises stress at that point D. So psi over g divided by frequency in hertz. We also have a relative velocity response function, a relative displacement frequency response function. Okay, so that's just kind of a quick look at the transmissibility. Then, of course, what we like to do next is our typical pattern here is we like to apply a PSD base input. So let's take we're going to do point D. That's where the action is, most of the action. I mean, there's action at all of those other locations as well, but the highest action response occurs at point D. And you can go back and verify that yourself. I'll save that as a homework exercise. So our input spec is navmat underscore spec. We've already preloaded that into MATLAB. So let's apply that PSD base input. It's as if we were mounting this plate on a shaker table and controlling that shaker to the navmat spec. So the point D response. So let's see, I kind of like to go through these backwards. Well, actually, starting with the first figure number. Here's our acceleration response, power spectral density. These coordinates refer to point D. And by the way, if you get kind of confused about the coordinates, if you go back to this plot here, you will find that if our x value is 0, so this is our x-axis here, and this is our x-axis here. Okay, the x-axis is along the fixed edge. The y-axis is along the free edge. So at x equals 0, y is equal to 4. That's this point, and it corresponds to what we're calling point D, and that's why we have x is equal to 4, y is equal to 0. Okay, I just realized I got that backwards. My bad. One more time. This is the x-axis, x is equal to 4, and this is going to be the y-axis with y is equal to 0. And having said that, I want to go back and double check that, and by the time you download this software, I may have rearranged that a little bit. But anyways, you get. But the important point is that this is point D, and that this is point D, and I think I need to go back and fix that in the software. So by the time you download the software, if you're running these exercises, I may have revved it so those coordinates get reversed. But let's not worry too much about that for right now. That's just my action item. This software that I'm writing that I'm presenting to you, it is everything. All functions are continuous process improvement, continuous work in progress. So I reserve the right to make tweaks and clarifications and adjustments. Okay, the relative velocity PSD, the relative displacement PSD. This is at point D, and our von Mises stress. Now our von Mises stress at point D is going to have an overall level of 210 psi RMS. So that's the square root of the area under the stress PSD, psi squared over hertz, and frequency in hertz. And just sort of, let's go ahead and I'll show you what point A is. Because I keep talking about how point D has more stress than point A. Well, what if we did go to point A? Let's see what we have here. So for our point A von Mises stress, and this I'm calling this coordinates 4 inches and 6 inches, so it's 4 inches along the free edge, 6 inches along the fixed edge. And again, I think I need to transpose those. But anyways, the important point I want to show you is that point A is 161 psi RMS, whereas point D, which is this outer lip that curves upward, is 210 psi RMS. So that's a little interesting characteristic there. Okay, so let's see what else we have here. So we've been through the PSD calculations for a base input PSD to our rectangular plate. And let's apply a shock pulse. So we have a shock pulse option to apply to this plate. So I'm going to hit return here because we're done with the, well, this was the transmissibility. But let's go back to this screen here. The Q value equal to 10 is already in our system here. So let's go to our arbitrary base input. Again, we're going to do point D. And in this case, we're going to have SRS 1000G _ Excel. That's the shock file that we called in earlier at the onset of this webinar series today. And let's see what our shock response is going to be for this plate. Now, again, this shock response spectrum, excuse me, I said earlier that the acceleration is applied uniformly about the perimeter, and that's not really true. It's only applied in this case about the two fixed edges, because the free edges are free to vibrate. So it's really the two fixed edges that have this base excitation, or more properly called an enforced acceleration. And it's even kind of tricky calling them fixed edges. They are fixed edges for the purpose of calculating the fundamental bending mode, but we're also applying a enforced acceleration. Let's see what we get for location D. So we run through, and let's go to our command window here. So our command window here says our peak acceleration in the time domain, 775.6 g, relative velocity 100.3 inches per second. These are all peaks. The peak relative displacement shown there, and von Mises stress. Let's just sort of do a little experiment here, a little side trip here. We'll go back and look at our plots here shortly. Let's see, how does this relative velocity peak relate to this von Mises stress peak? And again, this is all at point D. So we have, if we go to vibration data, structural dynamics, our stress velocity relationship. So we have English, we have aluminum, peak velocity, I'll just say 100 inches per second. And we've got a plate. Now, in this case, for our plate, we are going to have to come up with a proportionality constant. Now, we did have Hunt's plate relationship. We talked about a webinar or two ago, but that's really only works for simply supported plates. They're simply supported about all boundary conditions. So just sort of by some experience in previous runs, I know that about 0.12, I think, is a good proportionality constant to relate peak velocity to peak stress. Let's see if that works out. So we see 100 inches per second, maximum stress, about 6,100 psi, and that agrees pretty much here with our von Mises stress. Now, I suppose we could tweak this a little bit and try and get a little more accurate, but you get the idea. So, as far as the stress-velocity relationship and how it applies to plates, if anyone needs a good idea for their master's research or whatever, look at all the different boundary condition cases and come up with different proportionality constants based on the boundary conditions and material properties and so on. I'm still learning about this myself, and maybe someday I'll do that, but who knows. But to just kind of be aware that the stress-velocity relationship is out there, and that there is a relationship between stress and the peak relative velocity, or in shock sometimes we say the peak pseudo-velocity. Okay, what else did we need to do? We need to go and look at the tables. Where did our tables go? Our figures, I should say. I'm just going to hit recalculate here for point D. Okay, our von Mises stress time history. Von Mises stress always positive. Again, gets up to about 6,100 stress PSI. This is at point D. And again, I think I need to transpose those coordinates. The SYY, the SXXS, I don't know why that's a tongue twister, SXX. We have our response acceleration, our base input acceleration. Now this base input acceleration, you've seen this before because we've worked with this file several times. And it's just simply this SRS 1000G underscore Excel. So we synthesized it to match an SRS. And it kind of sort of, with some imagination, and if you kind of squint your eyes a bit and turn your head a bit, it kind of looks like a midfield pyrotechnic shock pulse. We also have our relative velocity getting up to about 100 inches per second, and our relative displacement. So relative displacement is important in some cases. For example, we're going to be looking at some Steinberg method for electronic equipment, particularly for circuit boards. And when we look at circuit board fatigue, which is going to be maybe in about 2 webinars from now or thereabouts, relative displacement is going to be our go-to metric. So that's an important metric. Relative velocity is important when we have our Howard Gaberson hat on and we're looking at the stress-velocity relationship, and we just want to take a quick estimate of what the maximum global stress is and calculate that directly from relative velocity with no consideration as to what the natural frequency is. Although to get this relative velocity, we did need to know what the natural frequency was. Response acceleration is always going to be important, especially imagine that we have, by the way, where'd that plot go? It's there somewhere. This is base input. I actually want to look at response acceleration. Where is it? Okay, what figure is it 21? Okay, 26. So sometimes I get a little bit confused or a little bit I get ahead of myself. Let's just recalculate, replot. Same plots all over again. Here we go. Here's our response acceleration. So imagine that we had some little piece part or some little miniature component mounted on that plate, and that plate was vibrating or it had this shock response. Then the response of the plate would then become the base input acceleration for that miniaturized component or piece part that was mounted on that plate. So acceleration response is an important metric. So all of these response metrics have their uses and have their places. And my approach is just to provide you with all the information, and then you can just take what information you need in whatever priority that you have. Of course, stress would be important if we were concerned about fatigue, for example, or we're concerned about yielding. Okay. So I think that pretty much is what I wanted to cover for the rectangular plate today. Let's do close all of that. I'll just close out of all those figures. And let's just briefly go through these slides. Now these slides here, these PowerPoint slides, these are just for reference. If when you're doing your homework, you can go back and make sure that you're on the right page and all that with the right numbers and getting the correct results. So this is how we calculated the natural frequency from the Rayleigh method with its corresponding mode shape. And then here's another look at that mode shape. Kind of looks like a saddle a little bit. And this shows a little bit more clearly this curved lip effect that I'm showing. I've been talking about. So due to this curved lip effect, again, the maximum response parameters are here, and due to symmetry, also here. So we entered in the Q is equal to 10 damping, and we saved that. Then we did our NavMat. Well, actually, we did our transmissibility plots, but just for brevity, I've omitted those from the PowerPoint files. But we applied our NavMat spec. That's our base input PSD. And we took a look at the response versus the base input. So really, anytime we take a plate and we excite it on a shaker, it is very common to see a tremendous amount of dynamic amplification. So I think that's about 14 or so dB higher in terms of the difference between the response and the base input. And you can verify that on your own, but tremendous amount of amplification occurring there. Okay. Now let me back up. Let's see. Let's just go ahead and do that. I want to make sure I'm not just spouting off some number here with. Let's see. Let's go to dB calculation for log-log plots, and let's do coordinates are the same frequency. And let's do GRMS values. Let's actually see what the overall level difference is between response and input. Okay, so it's about a 12 dB difference, or 11.5 dB difference. Now here's something interesting. If I put 22.9 here and 6.06 here, it's a negative dB difference. Now watch what happens as I swap those numbers. It's the same dB level, it's just the polarity changes. The important point is there's 11.5 dB difference in terms of overall levels from response to input. And that's how you can... We've done this type of calculation before. What I just ran you through was just a review exercise. Okay, so back to the PowerPoint slides. Okay, von Mises stress, PSD. And okay, this was doing the I need to change the title of that plot. It's not introduction. This is going to be for our shock input. Making changes on the fly. Okay, so here was for our shock input where we have this synthesized time history. And as you look at this PowerPoint slide, this is the old version here where I actually had the locations spelled out like quarter fixed length, half free length. And as I scratched my head and thought about that a little bit, I thought, yeah, that's not the most user-friendly way to present this those types of tables. So if we go back to where we were before, you can see I've already made a change in this process where I so this is actually the transmissibility function, but all of the base excitation functions for this boundary conditions. Instead of the old way I had it was just to spell out the location, but then I thought about, well, a better way is just to show you a diagram so you can visualize where those points are. So that's why you see a nice pretty diagram here. But in the PowerPoint slides, which I haven't gone back and changed yet, I still have the locations spelled out. Okay, so here was our base input acceleration, which is our synthesized acceleration time history. kind of looks like a midfield pyroshock. Here is the response acceleration. This is actually at our point D, which is that lip that kind of curves upward. Here is our von Mises stress. Okay, we're gonna shift now to circular bulkheads. So here we have some examples of circular bulkheads, and these are the types of bulkheads or plates, I should say, that I've dealt with before in previous phases of my career. And these are for rocket vehicles, and for small diameter rocket vehicles, particularly like sounding rockets. Now, a sounding rocket is an unmanned suborbital rocket, typically used for some kind of science project type research. And if you've ever tried to do a Google search on an image of a launch vehicle avionics, good luck. All that information is classified or proprietary or for official use only. But these universities get to do their little scientific payloads, and they're proud to display images of their scientific payloads on their web pages. And here's two scientific payloads, each having circular bulkheads, one or more circular bulkheads or circular plates for the avionics components. So if we were doing an analysis, what we would do is we would say, okay, we have these plates here, these circular plates, and there's so much mass riding on each plate or mounted to each plate. So then we would take that mass and then we would smear it uniformly over that plate. And here's actually from a launch vehicle provider that maybe is the lone exception here, where we get to see a circular bulkhead. This is from Armadillo Aerospace. This is from their website, so it's out in the public domain. And you can see this is a circular bulkhead. It's a circular plate with avionics boxes mounted on it. So one of our tasks might be is to predict what the response of this bulkhead is going to be under various types of base excitations, and then from that we would take the acceleration response of the plate, and the acceleration response of the plate then becomes the base input for these different boxes and components. And then we would take those boxes and components and mount them to a shaker table and do testing. So now if you're a deep thinker, you might be thinking, well, that's a little bit of hand weaving there, because there's those are lumped masses. They're not uniformly spread throughout the plate. And isn't there some mass loading effect of those boxes on the bulkhead itself? And the answer is yes, yes, yes. All of those are good concerns. But when we're deriving box level test levels, it's really important not to think too hard. Part of the reason is we have cost and schedule deadlines to meet, so we don't want to make this the subject of our PhD dissertation. So let's go to a circular plate. This is going to be a homogeneous plate, and I've got a path here at the bottom as to how to get to this dialog GUI here. We're going to have an aluminum plate. It's going to have a simply supported boundary condition, a 24-inch diameter. The thickness is going to be a 1/4 inch thick. And if this was a bulkhead, like as I showed you in the previous images, we would include the non-structural mass to be spread out uniformly. And just for brevity, I'm going to omit that, but you're welcome to put in a non-structural mass if you like. And from here, we're just going to go through the same sorts of things we did for the rectangular plate. So let's got to do a little bit of housework there to clean up some things. Let's go back to vibration data. So we're on structural dynamics. We'll go to that option. And we're going to go to plates, rectangular and circular. Let's go to circular plates. Now we have two options here. We're going to do a homogeneous plate, but I've also dealt with circular bulkheads that were honeycomb sandwich construction. And let's just say we'll do honeycomb sandwich at a later a future webinar. So let's just hit return here. Well, no, before we hit return, we're going to go to homogeneous. Okay, so let's do English, aluminum, material properties already accounted for, simply supported. Now, for the simply supported boundary condition for the circular plate, we're going to have multiple modes, and we can solve the governing partial differential equation exactly. We actually get a series type solution, but so because we're going to truncate our series at some reasonable number, it's not quite going to be an exact solution. But if we went out and included all the infinite number of modes, then it would converge to an exact solution. But anyways, it is solving the governing differential equation rather than the Rayleigh method. So 24-inch diameter, and let's see, quarter-inch thick. Okay. I think was it quarter-inch thick? Yeah, it was quarter-inch thick. Okay. Just reminding myself there. Let's calculate the normal modes and corresponding natural frequencies. There's going to be quite a few of them, so it's going to take a while. Okay, here's the fundamental mode. Now, the fundamental mode is where about 90% of the stress is going to take place. So all points here are moving in phase, upward. Or they would all, whether upward or downward, all points would be moving in phase with one another. And really what I had ought to do is animate these mode shapes so you could see this the shape going up and down, and I'll have to do that in a future revision. Let's see, a few other interesting things about this plate. Now, I'm not going to present myself as a stress expert because most people that deal with structural dynamics are more concerned with accelerations and relative displacement and not so much stress. But at the risk of embarrassing myself, I'm going to tell you what I think is going on with the stress corresponding to this mode shape. And that is there are two stress components in terms of the in-plane stress. There's a radial stress, so imagine the stress going radially outward from the center. Now there's also kind of it's called a hoop stress or circumferential stress or tangential stress. There's also a stress that goes around. So there's the radial stress and the stress that goes around and around and around. Well, I'll call it the hoop stress has an interesting characteristic. The hoop stress disappears at the center of the plate. So that's kind of like a singularity point, or whatever you want to call it, a point where there is no hoop stress. But then at all these other points, intermediate, and even out to this outer boundary here, there's stretching going on in the circumferential axis or tangential axis, whatever you want to call it. So there is hoop stress. So what does that mean? Well, because our von Mises stress depends on both hoop stress and radial stress, the peak von Mises stress does not happen at the center of the plate. Rather, it happens somewhere that's off-center. More about that later on. Of course, there's some higher mode things going on too that come into play, kind of as a higher order term type effects. It's also going to turn out for this plate where we have uniform base excitation that all of the modes that can be excited, and another word for that is all of the modes that have non-zero participation factors, but all of the modes that can be excited are axisymmetric. So we don't need to consider what the angle is when we look at the stresses and the response amplitudes, because it's all sweeping across 360 degrees, around 360 degrees, it's all the same for a given radius. So that's mode 1, the fundamental. Now mode 2 is a particular mode here that is not axisymmetric, and we have the same amount of mass going up as going down. So we got half the plate's 180 degrees out of phase with the other half. This mode cannot be excited by pure uniform base excitation. On the other hand, if there was spatial variation to that base excitation, or if there was an applied force with spatial variation, yes, this mode could be excited. But for our purposes, it has zero participation factor. It's of no further concern. Third mode shape is different, but same type of thing going on with same amount of mass going up as it's going down. This also has it's non-axisymmetric. It's going to have a zero participation factor. It's kind of fun, pretty to look at, but for us, it's of no further concern. Now this mode here is different. This is an axisymmetric mode that will be excited by uniform base excitation. And so we have some mass going up and some mass 180 degrees out of phase going down, but it's a different amount of mass in each case. And as I look at it, it's kind of fun sometimes to take these modes and give them names based on their shapes. So I used to live in Arizona, where we have a rather large Hispanic or Latin community, and we love to go to Mexican restaurants. And one of the Mexican restaurants we used to go to when I lived there, it was called Sombreros. So I think this kind of looks like a Mexican sombrero hat. So that's my little nickname for that. Okay, what else do we want to do with this? If we look at the command window, you can see all sorts of modes here. And I'm not going to discuss all the columns, but briefly, N is going to be the nodal diameters, K is going to be the nodal circles, PF is the participation factor, EMM is the effective modal mass. So we have N again is the nodal diameters, K is the nodal circles. So for our fundamental mode, 82.66 Hertz, the participation factor, that's the highest participation factor of all the modes, is 0.8414. And participation factors are calculated from the mode shapes, as well as the mass properties. The next two modes, which we've seen images of, each have participation factors of 0. They're of no further concern to us. Then our sombrero mode has a negative, what was it there? Negative 0.3487, its participation factor. It's the second highest participation factor. Now, the ones that have non-zero participation factors have one thing in common. That is, N is equal to 0. N is the number of radial or diameter node lines. So you look at the diameter node lines, and if diameter node lines is equal to 0, that means that mode is axisymmetric. And that also correspondingly means a non-zero participation factor. So the only modes we can excite with uniform pure base excitation are the ones with N is equal to 0, which are kind of few and far in between. but they're out there. Yeah, there's a couple of them buried in there. So from here on out, our analysis will only include the modes with non-zero participation factors. So let's apply our base excitation, and this is going to all be familiar to you because it's the same thing we did for the rectangular plate. Now here's one thing a little bit different though. For our amplification factor, we have two choices. We can just do a uniform factor, which is really the simplest and is very often what we choose. But if we want to go in and tweak the individual damping values for the individual modes, we could do vary by modes. And you can see there's only 4 modes represented there. Well, these are the axisymmetric modes that have non-zero participation factors. So if we have the time and inclination, we could specify differing amplification factors for each of those. But just partly for simplicity and partly out of laziness, I'm just going to say they're all Q is equal to 10. So we'll save the damping. And then that gets shown down here in the this little table here. It's good just to do kind of a spot check to say that, oh yeah, we got Q for all those modes. Q is equal to 10 for all those modes. I'm not sure what those other numbers are doing there. Let's see, transmissibilities. I'm going to go through this just kind of a little bit quick here because this is kind of getting to be about 1 hour, and I like to stop these at 1 hour. So we can do our center location. Let's go from 10 to 10,000 hertz. So here's the transmissibility for our center location, our von Mises transmissibility, PSI versus G. PSI per G versus frequency in hertz, I should say. And here's something interesting. If we go down here, we see at the center of the plate, we have 518 PSI per G at about 82 hertz, where our fundamental peak is. Well, that's at the center. What if we do the half radius location? How does that change? For half radius, that peak jumps up a little bit to 579 PSI per G. And my best explanation is because of the hoop stress contribution to the von Mises stress. So someone needs to fact check me on that. Okay, these plots here are just for the half radius location. You can see the relative displacement, relative velocity, frequency response function, and the acceleration transmissibility. So in this case, the origin is at the center of the plate, so R is equal to 6, is 6 inches out from the origin. Now, if you kind of go back here, and I need to add a few more lines to clarify what the locations are, but this is the half radius. So the half radius has, let's go to its acceleration. It has 10.94 G out versus G in, and 579 PSI per G. If we go back to the center location, it has a higher acceleration FRF, but a little bit lower stress level. And these are the levels at the fundamental frequency. So this is another example where the peak acceleration and the peak stress are not necessarily at the same location. They can be at differing locations, as is the case for this circular plate. Okay, so we've kind of been there, done that for transmissibilities. And I just saw a little non-catastrophic error that I need to fix. So I'm going to make a note to myself to fix that error message. But let's go and apply the navmat base input. We still have Q is equal to 10 entered in. So navmat spec is our base input. And let's look at the center of the plate. And we get our von Mises stress, power spectral density at the center. Our relative displacement, power spectral density at the center. R equals 0, that means the center. We've got a relative velocity response, PSD, at the center. Now let's take a look at this acceleration at the center. So G squared per hertz versus frequency in hertz. Obviously, the highest response is going to happen due to the excitation of the fundamental mode. But these higher modes are also coming into play and also contributing to the overall acceleration. So again, we get a tremendous amount of dynamic amplification going on. And just by some quirky coincidence of it appears that our overall response level is almost the same as it were for that plate we looked at earlier on. So it's about a 12 dB difference going on there. But this is what happens when we take, say, a circular plate and mount it on a fixture and do a shaker table test. Is we get tremendous dynamic amplification. And if you look, if we go frequency by frequency at all excitation frequencies, there is amplification greater than 1. So that's something we need to keep in mind, especially if we had, say, some piece parts or miniature components that were mounted or on this plate. We want to make sure, for example, that the natural frequencies of the individual components did not coincide with the natural frequencies of the plate. So say, for example, we have a bulkhead and we have a small avionics box. We'd want to make sure that the natural frequency of the circuit board inside that box did not coincide with any of these plate modes. And we also might want to think about, well, could we add some damping treatment to that plate or do something else to increase the damping because we're getting some quite high responses there. And again, each of these modes is a Q is equal to 10 mode, and you could verify that doing the half power bandwidth method. Okay, let's kind of move on here to our arbitrary inputs. So we're going to do our shock excitation. So our shock excitation for the circular plate, this will be, again, SRS 1000G _ Excel. And let's take a look at the half radius, because that had of the three locations that has the highest von Mises stress. Well, let's look at center first. So for the center first, let's look at its pseudo velocity or relative velocity. So its relative velocity is about 90 inches per second, and then you can see the von Mises stress. Now, this is at the center, and I need to go and put in a line there that says, yea, verily, that's the center. But let's see what we do for our half radius, same thing, at the half radius point. So for half radius, our relative velocity goes down, but our von Mises stress goes up. So let's go back to our stress-velocity relationship and see if we can make this work for a simply supported circular plate. And I'm kind of just doing this here kind of off the cuff here. It's okay. It's good to play around. Learn things by playing around. English, aluminum, plate. Put in our peak velocity there. And then we've got our peak stress value we're expecting at 4,125 psi. Proportionality constant. Let's try 1.2 again. That worked for us earlier today. A little bit high there, isn't it? Need to dial that down. Well, a little bit low. Okay, third time's a charm. So if we take our circular plate with simply supported boundary condition and apply a proportionality constant of 0.9, we can make that stress-velocity relationship come out. Now, some of you that are kind of thinking a little more deeply or thinking ahead might say, okay, maybe, just maybe, the peak stress occurs at the quarter radius point. Well, maybe so, and that could be kind of a homework exercise for you to go in and take a look at that, or maybe I need to go and put that in as an option. So again, I'm presenting all this software, these MATLAB scripts in this presentation today. By the time you actually download these and go through the exercises, these might be up to higher versions with more bells and whistles and a few little minor glitches fixed. But we've already been here over an hour, so let's kind of wrap this up here. As you go through these slides, this is just things I've shown you before. There's our famous sombrero mode. And just for reference, if you want to download the PowerPoint slides and go over them at your leisure, you can see how we did all these homework exercises. But all of this you've now seen before. And just one final note, I'm going to go ahead and upload this as being the official webinar unit audio-visual file, but I'm thinking about going back and making a few changes on the rectangular plate for how I do the X and Y coordinates. And then I already mentioned that instead of having to go through this verbal description of the response locations, instead I have that little image where you can pick off points A, B, C, and D. So that's something that's already changed. And that's all for now. Have a good day, and please email me if you have questions. We'll see you next time. So thank you and goodbye.